we really have, well, 3 lessons. I mentioned last week that this lesson on fission, fusion, and artificial transmutation traditionally in the past has kind of leaked over into the next class. I'm going to try to maintain focus today and get through this lesson today. There are certainly a lot of discussions we can have, and if we end up going in that direction, that's fine, then we will finish it tomorrow. But regardless, we're going to have lots of time for review here in this unit. We're looking today at fission, at fusion, and something called artificial transmutation. I guess just to begin with here, we're going to be applying the concept of mass energy conversion or conservation of mass energy to fission and fusion reactions, and potentially even to artificial transmutation reactions. Listen, any nuclear change, you should be able to apply delta E equals mc squared. If I tell you there's a nuclear change where, I'll even show it to you right now. I give you a nuclear change, and we're going to talk about this one a little bit later. And this is the nuclear change. Nitrogen 14 combines with an alpha particle or a helium-4 nucleus to produce oxygen 17 and a hydrogen nucleus, hydrogen 1 nucleus. And I tell you that it turns out that there is an increase in mass in this nuclear change, then you should be able to say to me, oh, that's an endothermic change. Energy went into the system to make that happen. And you should be able to, if I gave you the change in the mass, you should be able to find out how much energy was required to make this happen. And this will be an example. This is an example, by the way, of artificial transmutation. It's artificial because exothermic changes are natural changes where the mass goes down. This mass is going up. That doesn't magically happen on its own. What that's like is water molecules suddenly, for some reason, dissociating into oxygen molecules and hydrogen molecules. They don't do that because oxygen and hydrogen are less stable. Water is more stable. So something where the mass goes up is artificial in nature. So going back to my point here about what we are doing today with mass energy conversions, there's nothing really new there. You find a change in mass, you use it to calculate a change in energy. We're also going to be dealing, though, specifically with the details of fission and fusion. To begin with, getting to be almost 100 years ago, an Italian physicist by the name of Enrico Fermi discovered fission by bombarding uranium-235. So he refined uranium-235. When you get uranium out of the ground, uranium ore, very little of it is uranium-235. And by the way, uranium-235 is very stable. Very, very stable. And he bombarded it with a beam of slow-moving neutrons. Now, slow here is a relative word. We're talking maybe, I don't know, I'd have to look up some numbers, maybe 10% the speed of light. But they are slow enough so that when they collide with the uranium-235 nucleus, they don't just go right through. Because if they're moving too fast, that's what they will do. The neutrons will just go through the nucleus and not be affected. But they're not moving so slow that they can't penetrate the nucleus. So it's kind of a Goldilocks zone. It's kind of a sweet spot. Not too slow, so they're fast enough to penetrate the nucleus, but they're not so fast that they're just going to rip right through the nucleus. And what happens is, when that neutron joins the uranium-235, we can use a bit of our knowledge here about isotope notation. The 235 says there's 235 nucleons. We could look at our periodic table, and unless you remember, you can look up that uranium has 92 protons. So we're dealing with a nucleus with 92 protons and, I believe, 143 neutrons. 143. But then this troublemaker, this extra neutron, joins the party, so to speak. And what you end up with is something with not 235 nucleons, which is really, really stable, it turns out, but 236, which is incredibly unstable. So this is what happens. You get that, and that's not in your notes. I'm just pointing out to you that what you get when that slow-moving neutron enters a nucleus is you get uranium-236, which is incredibly unstable. This is not stable at all. And of course, things that are unstable change in nature to become stable. If I take a piece of sodium metal and I drop it in the bathtub, there's an explosion. There's a chemical reaction that changes the sodium metal to sodium ions. It produces hydrogen gas, which ignites because of the energy involved. And that combination of chemical arrangements of sodium ions and oxygen gas is more stable than solid sodium and H2O. And if you take Chem 30, that's a redox reaction. Okay? So it breaks apart. Now, what the products of this fission are depends on the energy involved of that neutron. It's not always that you're going to get these. So this isn't something you're going to memorize. The bottom line is that nucleus, which was stable, was poked to become unstable, and it broke apart into stabler things. It's, by the way, in Chem 30 you talk about catalysts, do you not? So we did have to add a little bit of energy to this to make it happen in the form of that energy of the neutron. But that just put it over the bump. When you draw catalyst reactions, do you draw it like this with a little hill going up and then down? That's what I'm talking about. We add a little energy, but then it goes way downhill. There's a huge loss of energy, so energy is released. It's exothermic. And, even though I will probably mention this in your notes in a second, the mass goes down. But notice, as well as getting these two large nuclei, which are smaller than the uranium-235, that's what fission is in general. You take a nucleus and you cause it to break into two smaller nuclei that are still quite large. You happen to get 3 neutrons. So it turns out that adding that extra neutron really upsets the apple cart. You end up with these two, the barium nucleus, the krypton nucleus, and you got some leftover pieces that make everything more stable if they're not in those nuclei. So this is the reaction that you're talking about in your notes. I'm just trying to impress on you again, there's something that happens, it's a very quick thing, nanoseconds maybe. But uranium-235 is not going to undergo fission on its own. Some people have a hard time understanding that fission is breaking apart. Think of the word fizz. When I pour Coke over some ice in a glass, it fizzes. The pieces of the Coke come out. It's breaking apart. So any nuclear change where we do that, we poke a nucleus, it's usually in the same manner with a slow-moving neutron, that causes that larger unstable nucleus to split into smaller fragments is called fission. And there is going to be a loss in mass in any fission reaction. And if there's a loss in mass, I hope you're comfortable now with the fact that if I say there's loss in mass, that means the mass is no longer there. It's not that there's some other particle unaccounted for somewhere. It's just less matter. Same number of nucleons, same charge, but it's less matter. And that change in mass is responsible for a release of energy. And just like you and I were talking at lunch, Charlie, that change in mass and the change in energy, whether you're talking half-life or radioactive decay like we were at lunch, whether you're talking alpha decay, gamma decay, beta decay, positron decay, whether you're talking fission, fusion, that change in mass is related to the change in energy by E equals mc squared. And I don't want to, crowd your brain too much, but that example I told you a few minutes ago where the mass goes up, well, this would be energy absorbed and mass gained. That's all. So that's fission. There's a diagram of it. But what's worthy of note is that those 3 neutrons that are produced happen to have just the right speed to penetrate other uranium-235 nuclei. And what happens is you get one nucleus which absorbs a neutron, and you get 3 neutrons coming out of it, which will cause 3 nuclei to absorb 3 neutrons, which will produce 9 neutrons, which will produce 27, which will produce 81. It's exponential growth, or geometric progression, if you like. And it happens very rapidly. This is the concept behind a fission bomb. All you need in a fission bomb is a chunk of uranium-235 or maybe some other material, and you need a trigger, which is, believe it or not, a single neutron. Now, given the cost that would go into manufacturing a fission bomb, I don't think you'd rely on one neutron, right? You'd probably have backup there. You don't want the thing to hit the ground with a thud. That's not the purpose of it. We want it to hit the ground with a thud, but the people who design these design them for maximum damage. I would have to look it up, but I don't know what you're taught in social studies about the 2 nuclear devices that were detonated over Japan. And I say over because they don't hit the ground. They're detonated above the ground. One was affectionately called Little Boy, and one was called Fat Man. And I believe, I can look it up and we can have a discussion in detail later. I believe Little Boy was a uranium device and Fat Man was a plutonium device. I'm going by memory here, but I think it was roughly 13 kilograms for one of those 2. I'm telling you 1 kilogram of uranium-235, if we hit it with a neutron and we just stepped back for less than a second, the chain reaction would cause all of the nuclei to go, and you'd release about 10 to the 13 joules of energy. Have you heard the phrase a kiloton in terms of explosive matter? A kiloton is 1,000 tons of dynamite. And I think we worked it out one year. It would be a pile of dynamite that would fill half of this room. So that's 1 kiloton. When you start talking nuclear devices, they release 14, 15, 20, 30 kilotons of energy. And that's not like dynamite. That's not like 30 of these piles. It's 30 of these piles in an instant. It's not a chemical reaction. It doesn't take a while for the energy to transfer from stick of dynamite to stick of dynamite. It's just boom. So very, very damaging. If you can regulate the process, then you have a fission nuclear reactor. Don't forget, from a previous unit, you generate electricity by turning a generator. Right? Coils of wire moving around magnets. So all you need is some energy input that causes that turbine or that generator to spin. How nuclear power plants do that is the same as how hydroelectric plants do it. They have something physically hitting the turbine to spin it. In the case of a hydroelectric, it's water falling off of a dam, spinning the turbine, producing electricity. In the case of a coal-fired plant, which we rely a lot on in Alberta, we burn the coal and the chemical energy is used to heat water. The water turns to steam. You point the steam at the turbine and it spins. I mean, that's oversimplified, right? There's not a guy holding a thing of steam pointing it at. It's technologically more sound. Here, the heat generated is used from the nuclear reaction is used to create steam to turn a generator. Regardless, and this is an important thing that you need to know. Why is it important? Well, I think socially speaking, it's important that you know this, but it's also something you're asked on exams. We have never discovered a fission reaction in which those 2 main products are not radioactive. They're always radioactive, which means they're hazardous. Right? They get into the food chain. When you start talking about what we were talking about with the play of the Radium Girls, when you ingest a radioactive material, it stays in your body for your lifetime where all of those particles, alpha, beta, gamma, whatever, are coming out and damaging you. Well, when this barium and krypton is produced, it's produced with a lot of energy surrounding it, and it's pulverized into a very fine dust. It's not like there's lumps of it laying around. Anybody heard of black rain? Black rain is literally the radioactive materials that are produced getting into the water cycle, and when it rains, the rain is black. It hits your skin, and it's only happened once in our history as far as we know. Well, twice. Hiroshima and Nagasaki were where the two bombs were detonated. But it gets in the water. It gets in you. You can't avoid it. So there's the sheer destructive power, and then there's the long-term effects. So what do we do with fission power plants? If the material is radioactive, how do we get rid of it? We dump it in the ocean. We seal it inside of a barrel. We fill the barrel with concrete. We line the barrel with lead. We seal it up really good. We ship it off in the middle of the ocean, and we kick it over. What else are you going to do with it? The half-life of some of these things is millions of years. There's nothing else you can do with it. Sometimes they're buried in mountains. Some people have said, well, why don't we just put it on a rocket and shoot it out into space? Yeah, and then the rocket explodes on liftoff, raining all this stuff down on us. It's not a very sound, it's not worth the risk, right? Yeah, we could fire it into the sun. Okay, does anybody have any comments about fission? All right, fusion. Fusion is in some ways the opposite of fission, but in many ways it's the same. And we'll get to the similarities and differences in a bit. But what fusion is getting nuclei to fuse. So sometimes a single nucleus like uranium-235 is more stable if it's in smaller pieces. And if it is, then fission happens. But sometimes smaller nuclei are not as stable as when they are together. So the reason why fusion happens is for the same reason that fission happens. It becomes more stable. But there's a catch. Same with fission. Fusion requires, I won't get there yet. Fusion produces a large amount of energy because mass is lost, so that's similar. And the energy released is because of a decrease in mass. Let's talk about the fusion reaction, the primary fusion reaction that happens on our sun. It's not the only fusion reaction that happens, but most stars have fusion of hydrogen. Specifically, tritium, which is hydrogen 3, and I'll show you the formulas for these in a second, and deuterium, which is hydrogen 2, collide and come together to form helium. Let me show you the reaction first. To form helium and a neutron. Now, the neutron is dangerous. There is such a thing as neutron damage or neutron radiation. So that needs to be absorbed, but it's very easy to absorb that neutron radiation. There's nothing radioactive. Helium, and I forget who was asking, it might have been you, Cyrus, about noble gases. Who was, no, it was noble gases. Helium, not only is helium chemically stable because it's an inert gas, but the isotope of helium that's produced here is non-radioactive. So this is clean. You got to deal with that neutron, which is not a major thing. It's clean. In fact, believe it or not, we have a shortage of helium on the Earth right now. It's because it's manufactured for the purposes of balloons, literally, and other things, and it ends up being used up in that way. And it's released and vented through our atmosphere and everything. So if anything, we could we could have more birthday parties and stuff with this, right? It's nice and clean. And the hydrogen that you need, unlike uranium-235, which is expensive to get out of the Earth, 3/4 of the Earth is covered in ocean water. Just use a chemical electrolysis procedure to extract the hydrogen from the water. It's cheap compared to the energy you'll get back. So why don't we have fusion nuclear reactors? Well, there's a reason for that. And when I was your age in Chem 30, I remember Mr. Barrington saying, you know what? When you're my age in, say, 30 years, Everybody will have fusion reactors everywhere. You'll have a Mr. Fusion in your house and in your neighborhood, and you can just dump whatever you want in it, kind of like Back to the Future, and you will get, we won't have to pay for energy anymore. And every time you read about fusion and where it's at for nuclear reactors, they say, it's in 30 years. In 30 years it'll happen. And 30 years later they go, in 30 years it's going to happen. Why do you suppose it's difficult for us to get hydrogen to fuse? The hint is kind of up there. They need to get within a femtometer for the strong nuclear force to attract them. But right now they're positive. They're positive and they repel each other. So it's not like I can just dump a whole bunch of hydrogen into a vessel and say, all right, you guys, go, join together. They have to be moving so fast, otherwise they just do this. They just repel away from each other. And it turns out they have to be moving so fast that you have to heat the plasma, it's called, up to the millions of degrees temperature. And I don't care at millions of degrees if you're talking Celsius, Fahrenheit, absolute value, who cares? It's really hot. So whatever you're trying to store this in vaporizes. The research right now is using magnetic fields to contain it. But we're not at a stage, there was a news story maybe 3 years ago about how this exciting discovery that they got a sustained fusion reaction happening for a period of time. And you looked at the data and the period of time was like a millionth of a second. And the amount of matter was a microgram. So it's very far off. How does the sun keep all of that hydrogen together?
It's so big, the gravity.
It's gravitational force that's holding it together. So since they're both positively charged at tiny distances, they will repel a lot. You need a lot of energy. Lots of energy. In fact, how many of you have heard of a fusion bomb? It's called an H-bomb. It has a vessel of these materials. You can't just look it up online and see exactly how it's made. They keep that kind of stuff secret. Okay? But it has a vessel with all of the hydrogen, the isotopes of hydrogen. And you know what they use to provide enough energy for the hydrogen to fuse? A fission bomb. So the fusion bomb has as its trigger a fission bomb. And the fission bomb will light things up to a high enough temperature that then the hydrogen will fuse. So it's a double whammy. That's the main reaction. By the way, helium will fuse with helium to produce bigger elements, on and on and on and on. So that's the graphic of it. Humanity has never detonated a fusion bomb on itself. They have done fusion bomb tests in the middle of the ocean and various places. Does anybody have any questions at all about either fission or fusion so far? Okay, let's turn the page. There's a lot of information here. We'll get to the calculations in a bit. I've changed my note package and I took a quick look before class today. The information I have up here is the same as the information you have, except that it might look slightly different in how it's formatted. Don't worry about that. I want to walk through all of these things together, piece by piece. The first thing to note is the main difference between fission and fusion, kind of in a qualitative sense. Fission involves a large nucleus that's not stable breaking into smaller nuclei that are stable or more stable. As far as I know, and I didn't take a lot of nuclear physics, as far as I know, all of these large nuclei that undergo fission need a trigger. They need to be poked with a neutron. And as far as I know, every single one, whether it's plutonium or uranium, they will produce more neutrons that cause a chain reaction to happen. Whereas fusion involves taking smaller nuclei. See, this is the trick with fusion. The amount of energy that we have to put in to raise the temperature to that value where it's going to happen as well as trying to hold the fuel someplace, the amount of energy we're putting into getting it to start is more than any energy we're getting out. We need to think bigger somehow. You need, well, gravity, right? You need a sun. And I always just say, why don't we just use solar energy? I don't get it. There is enough solar energy hitting our Earth at any time to solve all of our energy needs, all of them. All you need are photovoltaic cells, the photoelectric effect, solar cells. I don't get why we don't invest more research into that. Anyway, I'll get off my soapbox. Fission reactors are being used currently. They're becoming more and more popular. Not like popular is the wrong word. They're more frequently used. Okay. There are accidents from time to time. You have heard of, maybe you haven't, 3 Mile Island. Chernobyl, I'm assuming you've heard of. Fukushima. There is risk with anything. By any reasonable measure, there have been more fatalities caused by general run-of-the-mill electrical generation plants than there have by any nuclear plants in the history that we've been doing this. I mean, I don't know whose brainchild it was to build a nuclear reactor on an earthquake zone in Japan. I don't understand that. That was a mistake, okay? But you can avoid those mistakes. You can be smarter about it. Fusion reactors are experimental. The products for fission are radioactive, and the fuel is limited. There's not a lot of uranium-235 or plutonium, I don't know the isotope number, out there. And it's very expensive to refine, whereas the products are clean for fusion and the fuel is abundant. But there are some things that are the same. Each of these reactions lose mass. Each of these reactions are exothermic. And each of them involves more stable things being produced, which means the binding energy of the products is always higher. They're held together better. So now, before we grab our calculators and do some calculations, does anybody have any comments or questions about either fission or fusion? No? All right. I'd mentioned before, this is a binding energy graph. We've seen this before. I'd mentioned before that things that are stable are things with higher binding energies per nucleon. And I mentioned that things like uranium, large nuclei, end up, migrating is maybe the wrong word, end up finding their way through nuclear processes closer to the top of this hill, and smaller nuclei like hydrogen and helium end up migrating or finding themselves to the top of the hill through nuclear processes. The nuclear process on the left is fusion, the nuclear process on the right is fission. So, example, use the data shown below to determine the energy released when one uranium-235 nucleus undergoes fission according to that reaction. I really feel as though you know how to do this. What we need to do is find the total mass of everything we started off with and the total mass of everything we end up with and compare the masses. And if those masses are the same, then I've made a serious blunder in typing this out, because that would mean the reaction doesn't happen. Nothing is more stable than the other, so it wouldn't happen. So that's what we're going to do. And I'm going to give you a minute. I want you to find the mass of the reactants and the mass of the products. So the reactants are a uranium-235 nucleus and a single neutron. The products are the barium nucleus, the krypton nucleus, and 3 neutrons. I'm sorry, I didn't explain that. That 3 in front is like a coefficient in a chemical reaction. It just means you've got 3 of them. So if you were to try to balance this, you would need to recognize this is 3 on the top because it's 1, 1, 1. So I'll give you a minute to do that. I'll do the same thing. Okay, so you should have no problem finding any of those values as long as you take your time and double check your entries before you hit equals. Piece of advice, you never know when you might make a mistake. I'm getting for the mass of the reactants, which is a way of saying what we start off with here, and for the mass of the products, this number here. So what are we going to do with that? If you're trying to find the energy released, and this is just one nucleus, then you have to take the final mass minus the initial mass, and that will be your delta M. And then you have to set that as your delta M in the formula E equals mc squared. And again, you guys, in all seriousness, that's where you're going to make a mistake, right? You're gonna put a decimal in wrong, or you're going to forget a negative like I did earlier. The concept itself is not difficult. The execution can be complicated, right? So I'm going to take my final mass, which is this, and I'm going to subtract my initial mass. I better just type it in. And I'm going to subtract my initial mass of 3.9199649 multiplied by 10 to the negative 25. Step back and look at that. I think that looks fine. And we're getting this number for the change in mass. I find maybe in online sources and in textbooks, they don't worry too much about final minus initial. I like that. I like that we get a negative delta M. That tells me that mass is lost. And when I multiply that by the speed of light squared, I get negative 2.79 times 10 to the negative 11 joules per nucleus. Per nucleus, right? If you want to write that down in joules, that's fine. If we convert that to electron volts by dividing by our conversion number of 1.6 times 10 to the negative 19 joules per eV, we're getting 174 million electron volts of energy released for every nucleus. I don't want to turn this into a chemistry lesson, but a mole of uranium-235 would have about 235 grams. You could hold it in the palm of your hand. Well, you could hold, it's pretty dense stuff. You could hold it in your hand. 235 grams of it. If we multiply this by how many nuclei there are in a mole, just for kicks, there's 6.02 times 10 to the 23. I think that's right. I'm pretty sure. No need to check. This would be the energy in electron volts released. And by the way, even if you go with joules, it's still a boatload of energy, right? This isn't just a lot of energy for a nucleus. This is a lot of energy. 10 to the 13 joules. Any questions with the calculation there? Let's do the same thing with fusion. So I'm going to give everybody a couple of minutes here. I want you to just do the whole thing. I'll do it up here as well. We want to find the change in the mass. Then we want to multiply that change in the mass by the speed of light squared to get the change in energy. I'm getting, for a change in mass, negative 3.14 times 10 to the negative 29 kilograms. I think that's smaller than it was in the previous example, but keep in mind this is less matter. And multiply by the speed of light squared. whoops, multiply by the speed of light squared, which is 3 times 10 to the 8 squared, giving me about 2.8 times 10 to the negative 12 joules. And again, what you choose to record your answer as joules or EV is up to you. I think this is trivial at this point. There's a bigger picture coming around the corner in a second. If you do want to work it out in electron volts, it's about 17, 18 million electron volts. This isn't for a single nucleus. This is for the two nuclei coming together. Okay? And that's a lot less energy than the number we got in the previous question, which was, I think, 170-something million EV. But, and I will make this point officially in a second, this is a lot less energy than the fission of 1 uranium-235, but 1 uranium-235 has a lot more mass in it. There's less fuel here, but we're getting a really significant amount of energy still. So these are the numbers from our calculations. I'm pretty sure. I changed my note package so we didn't have to keep flipping back and forth here. So for the fission of uranium-235, we got in the neighborhood of negative 174 million EV. And for the fusion of the hydrogen for that reaction, we got in the neighborhood of negative 18 million EV. How much is it if we look at maybe joules per kilogram, which is a better assessment of how good these processes are at producing energy? Right? So per kilogram of fuel. Well, if we take, and I've already added up the masses of the reactants for us, this number is the uranium-235 plus the neutron. If we take our joules of negative 2.7918 multiplied by 10 to the negative 11 joules and divide by this many kilograms of fuel, 3.919649, 3.919649 times 10. That can't be negative 29, can it? It's negative 25. Yeah, it's negative 25. So I'll have to change that in your note package. I'm assuming that yours actually says negative 29 as well here. It should say negative 25. What we get is that many joules per kilogram. And I don't care about the exact numbers here. This isn't going to be my point. You get in the neighborhood of 7 times 10 to the 13 joules per kilogram. Let's calculate it over here for the fusion. Let's take the energy released by the fusion reaction in joules and divide by the mass of the two hydrogen nuclei together. Negative 2.826 times 10 to the negative 12. It was less energy. It was less energy. Divided by, but it's less mass, 8.3526 times 10 to the negative 27. So I'm taking the energy in joules divided by the mass in kilograms, just double checking the numbers. It's more. This is a huge advantage with fusion as well. If we want to get fusion reactors going to help us live, because we're running out of fossil fuel. Again, I think we're going in the wrong direction. Solar is better, I think. Then again, I hate to get off topic here. Solar is expensive, and the materials we require for solar cells are hard to get. They're not abundant. So there's problems no matter what. If we're going to live on the earth, we're going to wreck the earth trying to survive. somehow. Boy, that sounds cynical, doesn't it? Anyway, it's more per kilogram, 3.4 times 10 to the 14 joules per kilogram. You could do it as well by taking the electron volts divided by the nucleons. That would work as well. I'm not going to do that. Do you get my point? Fusion has, you got to be careful. If you're given two reactions, a fission and a fusion, the fission produces more energy, period, always. But per unit of fuel, the fusion wins out. Let's talk about chemical, which is how we get most of our electrical energy. When you burn ethanol, you get about 1.4 million joules of energy. That sounds impressive. If you burn 46 grams of it. Compare the energy released by chemical, nuclear, and fission and fusion. Well, let's calculate what this is in joules per kilogram. Oh, that's pretty impressive. 3.0 times 10 to the 7 joules per kilogram. Am I reading that right? Okay. I'm going to be very liberal with my analysis here. 10 to the 7 joules per kilogram for chemical. 10 to the 13, and I am being liberal here, 10 to the 13 for fission, 10 to the 14 for fusion. I hope you understand that this number that I'm pointing at with the fusion is not actually 10 times greater than the number on the left. But some of them would be. So we're talking about a comparison here where the most energy is in the neighborhood of 10 to the 14 joules. This is joules per kilogram, and this is fusion. 10 to the 13 is fission, and 10 to the 13 is about a tenth of 10 to the 14 in terms of these numbers. That means fission is here at 10 to the 13. Where would 10 to the 7 be? You can't even put it on here. It would look like it's at 0. 10 to the 7 is 1/1,000,000th of 10 to the 13. So you would need to scale this so your bottom line is 1/1,000,000th of that distance between the fission and 0. So this is chemical. Nothing. It's hardly anything, right? Any questions about any of those calculations? Okay, as I said, and I have a good context to help you wrap your head around this. Remember when I told you about me going to get that nuclear scan? And I said, well, somebody was at the U of A calling me a couple of times to confirm that I would be there because they were making the stuff. They were making technetium-99m, which is not stable. They were making something through an endothermic process so that then it could decay, and they used it in order to scan me. That's what artificial transmutation is. I have a friend, we don't talk very often anymore, but I went to high school with him. We were quite close in high school. He's a nuclear physicist, and he works at particle accelerators throughout the world. And he gives presentations to students in Europe. And when they ask what he does, these are usually elementary kids, he says, I smash things together and see what happens. And they can't wrap their head around that. And he says, well, it's like I smash cherries and grapes together to see what I get. And sometimes I get oranges and sometimes I get apples. That's what's happening here in a particle accelerator. Physicists slam stuff together to see what's produced. So this particular illustration, nitrogen-14 plus alpha particles produces oxygen-17 and hydrogen nuclei, is just one example. I don't know what the artificial process was to produce the technetium that they injected me with, but they used a particle accelerator and a beam of particles was continually hitting, producing this technetium, which through the mystery of physics and technology they collect, I don't know how, and then they put it in a vial. It's pretty amazing. These can be endothermic or exothermic. And I never used to do this, but a student had asked one year, is that example you just gave us, this nitrogen thing, is it endothermic or exothermic? And I said, I don't know. So we looked up the masses of all of these. These two masses on the right are the masses of the oxygen-17 and the hydrogen-1, which is just a proton, by the way. These two masses are the masses of the nitrogen and the helium nucleus, or alpha particle. This is a good exam question. I give you all this. I say, is this an exothermic or endothermic process? What are you going to do? You're going to find this mass total, and you're going to compare them. If you have more afterwards, it's endothermic. And you will. I'm not going to go through the calculations here, but if you add them together, you will get more mass afterwards than you started off with. I don't know that it's going to be by much, but it will be. So that's my presentation on fission, fusion, and artificial transmutation. Any questions at all? Yeah.
Can you use fission on something that's not radioactive?